welcome in. You are probably here because you wanted to see the kind of derivative of the function e to the x. So it's one of the most powerful functions that we have in sciences. It is definitely utilized quite heavily if you do go on into mathematics or sciences, for example, engineering. You start talking about things like differential equations, which in high school are meaningless to you. So you kind of want to try to see if you can build up the foundations, and this is definitely one of the foundations. So that's why I am presenting it here, just to give you a glimpse of the derivative of e of x. It has an extremely special derivative, and that particular derivative is that if you're going to take the function e to the x and take its derivative with respect to x, you will notice that you're going to get the function back. And that's what makes it really special. You don't really have functions that spit out the derivative and it's exactly the same function. So, the first derivative is e of x, okay? The second derivative is e to the x, and so on. And that's pretty remarkable, and it is utilized quite heavily. Now, why does this come about? Well, we can certainly try to show it, and I'm going to do that. I'm going to try to show it to you visually, with a little bit of kind of a hint, okay, in terms of how you can think about the visual representation of it, and then I also will show it to you, okay, by utilization of the fact that an exponential, so e to the x, or e to the anything, okay, can be captured by power functions, so the sum of power functions. So let's dive in here. If you're going to be taking the derivative, I'm going to start from first principles so that it's not anything beyond us. So we would have that this is the limit as h is approaching to 0 of a function where you substitute the argument x plus h minus f, okay, at x, and then divide by h. And then of course the problem is, because you are setting h approaching to 0, then this becomes kind of a 0 over 0, an indeterminate format, and we want to be able to see what that limit is. So this limit is the derivative or the slope at any particular point of the function. So e of x is actually defined everywhere. It's not a very complicated function. So let's take a look if we can massage this. Now I'm going to drop, okay, this limit for the moment so that you kind of don't worry about it. I will bring it back. I just want to concentrate on this right here. So let's substitute everything in here in terms of our function. So this would have been just e. This is x plus h minus e to the x, and this is all over h. Now, massaging this, so if you look at the numerator, I can actually do the following. So this is e to the x, and then multiplied by e to the h, right? So this is just simple exponent rules. So I have this right here. Now, why am I doing that? Because I want to be able to take out this right here from both of the terms in the numerator, which I can do so. So that's going to give me that. And what I'm going to have left behind is e to the h minus 1 all over h. And now if I bring my limit back, so this is now my limit, I can bring it all the way back in here. And what we will find is that this is the same thing by applying limit properties. So I can bring this, okay, outside of the limit because it's not dependent on h. And then I can bring the limit back in here. And now what I have is this problem. Now, as limit of h approaches to 0, and you just kind of blindly substitute it back into here, you will notice that e, okay, if h was 0, would have been 1. So it's 1 minus 1, which is 0. And then in the denominator, h is 0. So you still have a problem of having 0 over 0 there. Now, what we want to be able to kind of see that this is actually equal to 1. And it is, in fact, equal to 1. So first I'm going to show it to you just visually. And you can probably kind of deduce it as well if you were plotting this out, and that's what I want to be doing first. And then I'll show it to you algebraically in just a moment. So let me bring up kind of Desmos in here. So I'm going to pop that up, and I'm going to set this particular kind of limit. So let's call this, I don't know, G. Okay, I guess it's of H is equal to, and what I have is e to the H, and this is minus 1. If this was it, then this is not very difficult for us to visualize, you know, especially if you've done functions. Notice that e to the H and then minus 1, it's just a transformation and brings the actual e to the H 1 down, right, on the y-axis. So that's what we see there. That's why it's going through the 0. But now notice that if you take this and you divide it by H, right, which is exactly what we have, so it kind of shifts back over, and really we just have a hole, and that particular hole is going to be at 0. So if I go back in here, you'll see that it's actually undefined there. So we have a hole right here. But we are interested in the limit, of course. So the limit as H tends towards 0, H is really never 0, right? So it's just simply, okay, some kind of a very small number. So if you're approaching it from the left, okay, so you'll notice that this particular function, so as you're approaching it from the left, it gets closer and closer and closer to 1, as you can see there. So from the left-hand side, the limit is actually, okay, as you go in here, it's going to be equal to 1. And then from the right-hand side, you're going to see, okay, that the limit is also equal to 1. Well, if the limit from the left and the right are equal, then we know that the limit exists. And in this case, we can see visually that indeed it is equal to 1. Now, you can also, you know, substitute in here. So you can say, all right, so this is going to be G, okay, and I want to be able to substitute for some small number. So as you make this, let's say, smaller and smaller, for example, so on the positive side, so I'll just put it at 0.1, okay, you'll see that. And then if I just make this smaller, so let's say 0.01, 0.001, you're noticing it that indeed it just gets closer and closer and closer and closer, okay, to 1, okay, as you're going through there. So you can see that. Now you can also substitute it, okay, from the left-hand side. Okay, so that's going to be negative, right? So 0, let's say 0.1 right there. And again, it can get closer and closer. So right here, you can see there, it gets closer and closer to 1. Okay, 0.999, etc. Okay, and then now it's actually kind of swapping in between because, you know, Desmos is just calculating and then approximating it there. So that is the visual representation. So you can see that e to the h minus 1 over h is actually the limit is equal to 1. And if that is the case, then we can see that this entire thing, well, e to the x times 1 is just this, which is exactly what the derivative we set out to have. Now, if you're not satisfied with the visual representation of the proof, then you can take this right here, and you can do it algebraically. So I'm going to show that to you in just a moment. So here, this is what we want to do, as h tends towards 0, we want to show that this indeed, okay, is basically 1. So the limit is 1. So how do you do that? So I'm going to kind of refresh you back, and I'm going to use that e to the h is actually equal to, and this is the same thing as the summation, okay, this is of k equal to 0, and it goes to infinity of, and this is going to be, I guess, h right here, okay, to the k divided by, right, k factorial. Now, if you've never run into this before, so you can represent an exponential function as a sum of power functions. I've done a video on that, and you can see that video up above there, okay, so if you like. And in that video, I kind of go over and then show you also visually, okay, how the two actually are identical. Now for here, if we know that e to the h is indeed equal to this, if I expand this out, so notice what's going to happen in here is I'm going to get, Okay, so for k is equal to 0, I'm going to get h to the 0 all over, okay, 0 factorial, plus, and this is going to be, you know, h to the 1, okay, divided by 1 factorial, and then h to the 2 divided by 2 factorial, plus, and so on, and this continues throughout. Now, of course, this right here, so h, although it tends towards 0, it's never 0, right? So it's just always some number, okay? But it's never 0, it tends towards it. And therefore, h to the 0 is just 1. 0 factorial is 1, so this is just 1, plus, it's going to be h over 1. It's going to be h squared over 2, plus, and then so on. I'll put dot, 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 okay, within here. So that is what this is equal to. Now, we have right here minus 1. So I'm just concentrating on the numerator. So if I take this and I subtract 1 from it, well, that means that the first term, okay, is going to cancel with this term. And all I'm going to have right there is then this is going to be just h, right, which is this term, plus h squared over 2 plus dot, dot, dot. And that is what this numerator would be. Now, if I take h right here, when I'm going to divide by h, so if I take this whole thing and now divide it by h, well, what do you notice? So I can certainly take out an h from here. So this is going to be h, okay, and then this is going to be 1 plus. And now right here on the second one, this is going to be just h, no longer h squared over 2 plus, you know, dot, 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 etc. And this is supposed to be divided by h. Well, what happens? Well, this h and this h cancels. And now as I take the limit, as h tends towards 0, well, the limit of this, well, is just going to be equal to 1. Because this is going to tend towards 0, and so will all the other terms because they have an h in it. And it's in the numerator. And that is how you can algebraically show that indeed that limit is equal to 1 if you do know and are familiar with this sum of power functions for the exponential function. So there you have it. So that is the derivative of this powerful function. Now I hope that you're going to see it because I'm going to also use it in other proofs for the general case of the derivative of an exponential, not necessarily where the base is equal to e. Well, the base is going to be anything that we like. So I'll do that as well. All right. Okay, so thanks for watching. I hope that this made sense and you have now actually found the derivative of the most powerful function that we actually have within kind of very applied sciences. Okay, thanks for watching. See you in a future video. Bye, everybody.